I'm Mike Johns. I'm a data scientist at HelloFresh. Thanks for coming. I'm going to talk about propensity score matching, which is a non-experimental approach to trying to accomplish causal inference. Just a little bit about myself. Data scientist is now the fourth leg in a very long career I've had using data and analytic methods to answer questions and solve problems. I started off as an experimental psychologist, torturing undergraduates and p-hacking a lot. I went on to epidemiology, worked for the city for many years, did policy research, and most recently have made the leap into data science proper. So this is a topic that comes from my home field of the social and behavioral sciences. So just a quick outline. I'll start off with a kind of overview, propensity score matching in a nutshell, and then get into the specifics. Talk about how to calculate a propensity score, which involves building a model, selecting covariates, how to use those scores to then perform matching in order to find a comparison group. And then if there's time, I'll briefly touch on estimating treatment effects. That's actually a pretty complex topic in and of itself that we could spend a couple of hours talking about. So I'll do a lot of hand waving there. Okay. So propensity score matching. This is a quasi-experimental method that is designed to help you find a control group in a situation where random assignment is impossible. So you're using this propensity to be exposed to something, let's say it's a marketing campaign, some new policy, some new law, as a proxy for assignment to a condition as you would in an experiment. So it's a pretty common method in social behavioral sciences, gets used a lot in educational research. Econometricians are probably pretty familiar with it. It was developed, the original theory was developed by Don Rubin and Paul Rosenbaum back in the 80s. So it naturally fits within the social behavioral science world. And it's basically founded on this idea that the key to drawing causal inferences is based on this idea for groups in a study, treatment and non-treated groups, to be balanced, essentially, to be equivalent on average. And this is an idea that comes from the potential outcomes framework that Rubin has also been heavily involved in. And so the idea is that you want exposure to be independent of any observed or unobserved background characteristics, right? So you can make an inference that any differences between groups are based solely on exposure to some treatment or condition. Now, this method is best suited for dealing with selection bias, which is just a pre-existing tendency to behave in a certain way, expose yourself to certain material, and so forth. It cannot necessarily eliminate other types of confounds. So the list I have here, history, maturation, regression, I mean, these are all have a temporal aspect to them, and so this isn't necessarily a solution to dealing with all potential sources of confound in an observational study situation. So let's say we have a situation I often find myself in. I work for HelloFresh, we sell food. Probably makes sense that we want to put some advertising up on the Food Network, right? And in the ideal situation, we would have some means of controlling who sees that ad, who doesn't sees that ad, and then maybe after some time, 7 days, 14 days, 21 days, we look to see of the people that saw the ad, how many show up as customers, and of those who didn't, how many showed up. And the difference between those two conversion outcomes ends up being our estimate of lift or a treatment effect. Unfortunately, the real world is not so convenient or cooperative, so oftentimes all we know is who saw the ad and who didn't. We had no control over whether or not they were assigned to see it or not. And so almost certainly we have a case where we have a confounding situation based on selection bias. So people who are interested in cooking almost certainly are going to be more likely to watch the Food Network, especially if they have cable, and then by that fact, more likely to be exposed to the ad. And almost certainly they're probably just more likely to become a customer of HelloFresh if they're interested in cooking, right? So this is the classic illustration of selection problem. So we have background variables. In this case, we have a latent variable that is related to both the chance of being exposed to the ad and the outcome itself. Now, typically, we don't have access to this latent variable. We have information about other variables or factors that are related to this thing of interest. So demographic characteristics, past behavior, psychographics that we talk about in the world of marketing. But what we really want is this situation, right? We want to sever that relationship between these confounds, these selection biases, and exposure to the ad, so that when we look at the difference between those people who saw the ad and those who didn't, we are not, that inference isn't going to be confused or confounded by the fact that the people who saw the ad are just different to begin with, okay? So those of you who are familiar with the sort of causal graph, the work of Judah Pearl will know this as the backdoor problem, right? So we want to shut that back door. And propensity score matching is basically just one way to try and accomplish this. So there's 4 key steps here. You first have to calculate the propensity score. So you're going to build a predictive model. And the model you're building is predicting the probability of exposure for both those people who, let's say in this case, saw the advertisement and didn't see the advertisement. Then we're going to use that score to create a matched control group for the exposed group. We're going to check that matching actually accomplished balance, right? It made the groups equivalent on average. And then we're going to estimate a treatment effect based on this matching. So for those of you who like equations or this kind of formulation, so propensity score is pretty simply just the probability of being exposed to some treatment, let's say it's an advertisement or what have you, conditioned on some set of covariates. So covariates basically means variables, features, if you like, background variables and so forth. So again, it could be average age in a household, number of people in a household, median income, things like that. And so it's basically you're predicting the probability of being exposed, and then you're going to use that probability to find what are unexposed units that are very similar to the exposed units. So basically, your goal here is to build a model of the selection process. And essentially, one idea that I really like is that what a propensity score is doing is it's taking all this background information, it's just condensing it down to one scalar, right? And that's actually going to make it a little bit easier for you to find similar people, households, units, and so forth. And what you're trying to do is, again, optimize balance between the groups, optimize average equivalence, so that you can make selection strongly ignorable in the words of causal inference. So for all the data scientists in the room, I will call out what you're not doing is trying to build the most predictive model that then is going to generalize to unseen data, right? It's a slightly different, what we're really building here is a descriptive model, not a predictive model. So just to illustrate that, on the left, you have your classic kind of machine learning ideal, where you have your positive cases, and ideally you have the probability mass pushed all the way up against 1, and for your negative cases, right, probability mass pushed all the way up against 0, and very little overlap here between the two groups, right? Now, I'm not saying it always works out this way. We would love it to work out that way, but this is what we're going for. In the propensity score situation, we're actually looking for some overlap. And you still probably want that unexposed probability pushed up against 0, but for your exposed group, it's almost ideal to have a nice spread across the different propensities. Because that space, that common support there, that's where you're going to find your matches for your exposed group. So when it comes to building this propensity score model, predicting who's exposed, who isn't, or predicting the probability of exposure, one of the key things that comes up a lot in the literature is in building the model is capturing the proper functional form of the relationship between these background variables on your population and the outcome. And so typically this is a question of, are there complex interactions that you're missing? Are there nonlinear relationships and so forth? Despite that, typically what people use is logistic regression. It's a pretty simple, handy tool. There's some limited research on more sort of traditional machine learning models, random forest and boosting. And typically it doesn't seem to give you any advantage, except in the case, maybe not surprisingly, if you have a lot of non-linearity, non-additivity, which are regression assumptions. So for the most part, logistic regression usually gets the job done. And then sort of jumping back a little bit in terms of thinking about how you're constructing this model and what's going into it. What are your covariates, as they're called? What are your predictors? So really, again, you're trying to build this model of the selection process. So your predictors should ideally be related to that selection process. And really, you're looking for what you could call true confounders, things that are going to predict exposure as well as the outcome. And generally, you also want to try to avoid what are called instrumental variables. The economists in the room will know what I'm talking about. So these are variables that are related to exposure, but actually not related to the outcome. And so, of course, this is a quasi-experimental method, and your ability to get a real unbiased estimate here depends on finding and including key variables or key features that are going to capture that selection process. So omitting variables is something of great concern. Now, generally, I would advocate when you're thinking about how do you build this model, what variables do you include, is really having a theory of selection, okay? So hopefully you have some domain knowledge, you have some domain expertise that you can draw on to think about the problem that you're faced with in terms of what are the characteristics of people or households that are going to increase the likelihood that they see an ad for your product and also just become a customer without exposure to any advertising. So along those lines, past behaviors are great to include, anything that happened before the exposure. Demographics, attitudes, geographic related variables. Probably one of the better ones is any pre-exposure values you have on the outcome you're going to predict, if that's possible. That usually is more relevant in a case, let's say, in a business case, maybe if you have a product that people purchase over time, multiple times. In terms of unobserved variables, and this is really the big shortcoming here is, by definition, they're unobserved, but this is where having a theoretical model can be helpful to think about what is it that's likely to create a selection bias, and try to think about, are there proxies for that data or that variable that I could use in the model? So the world I work in, the world of marketing, you have all these third-party data providers. They purport to give you data on things like interest in camping or interest in magazines or what have you. How good those data actually are is an open question, but there are potential sources out there that you could use to try and get to things that are more sort of latent most of the time. So interests, propensities, proclivities, things like that. So this next point I make very cautiously. So typically over-including variables is not going to be a huge problem because remember, we're not technically worried about overfitting here. That said, overfitting generally not a good thing. We want to be careful about multicollinearity. But this is a case where you can probably, if you're not sure, you want to over-include, here you can draw on more traditional data science or sort of statistical learning methods and use regularization, maybe do some variable selection, and then calibrate your probabilities just to be safe. Okay, so once you've built the model, you have your probability or propensity for your exposed group, your unexposed group. Now you're going to have to do some matching. And again, the idea here is that you have the population is scored, you match, and essentially you're trying to find this set of overlapping groups that have similar propensities, both in pairs and across the entire group. So the matching algorithms, there's a whole literature on this. We could spend an hour talking about different approaches. But the three core dimensions that you see are how greedy is your matching algorithm? Is it greedy or is it optimal? Whether you put constraints on the distance, so do you set a caliper or do you let it be open through nearest neighbor? And then symmetry, one-to-one versus one-to-many. Just quickly to walk through these. So in the greedy approach, right, you're just iterating through, you're looking for the best match, you're gonna seize on that, stop and exit. So in this case, if we imagine we were looking for a match that was in with about 10% of our exposed, and we started from the top, we might get to 0.5607, say that's great, it's in my range, I'm taking that one and I'm exiting. Even though technically the best match, the closest match might be down here. In optimal, we're looking to minimize the total within pair difference. So this is a more traditional optimization problem where you're gonna go through the entire list of exposed, you're gonna try and find the best match for every pair and then optimize across the whole group. Caliper versus nearest neighbor, this one's a little tricky. So caliper is basically just saying you're gonna set some defined limits on how close the match needs to be. So again, if we stick with an example, we're looking for, let's say about a 10% match. We could pick any of these 4 here highlighted as a potential match. Nearest neighbor, obviously you're looking for the closest match, but given the circumstances, you could end up with a very close match or you could end up with a very far match. There's no limit placed on how near or far the neighbor actually has to be. And then one-to-one, one-to-many, pretty self-explanatory. So the general recommendation that comes out of the literature, usually what people do, they match on the logit of the propensity score. They set a caliper, right? So they set a limit on how close the match has to be to, so the match in the exposed group, how close it has to be to the unexposed. And it's usually about 25% of a standard deviation. In terms of greedy versus nearest neighbor, or greedy versus optimal, there's not a lot of evidence on which one performs better and when. A greedy algorithm is going to give you better balance between groups, and that's ultimately what you're after. But there can be some instances where optimal is a better approach. And then really when it comes to one-to-one versus one-to-many, it depends on the support level in a lot of ways. So how much overlap is there between the propensities of your unexposed and exposed groups? So unfortunately, this is an area where there's really no sort of silver bullet or magic bullet solution. I don't know which one is the right metaphor. It's really gonna depend on your situation. It's gonna depend on how much the scores, the propensity scores themselves overlap, which is gonna depend somewhat on the class balance, imbalance, and then also the baseline difference between your covariates. How big are those differences in the two groups? So once you do your match, you have your exposed group, you have a matched group of unexposed that are now gonna be your control. So now you need to check to see, did the matching work? Did you achieve balance? Did you reduce those pre-existing differences on these covariates that you're using? So generally, you probably wanna avoid p-values in testing the difference between the groups. Generally, p-value isn't gonna answer the question you wanna know, which is, have I reduced the size of the difference? It's gonna tell you the likelihood or the probability that there's a difference this size or larger. That's not really what you wanna know. So generally, what people use is what I know as Cohen's D. It's also just called standardized mean difference. So you take the mean of your exposed group after matching, unexposed group that is matched to it, and divide that by the pooled standard deviation. And so you get a mean difference estimate in standard deviation units. It can be positive or negative. I usually look at the absolute value. Over here, down in the right-hand corner, just an illustration of what a Cohen's D of 1 looks like, what the sort of level of overlap is there. It's quite a lot of overlap. And like I said, there's no clear consensus, but 0.1 is usually a pretty good metric to use. But it can vary depending on your use case. So this is just an example from a recent match that I did. So here on the left is before matching. So these are just density plots for the unexposed and exposed group. Very similar to the ideal that I showed you earlier. This is totally coincidental. Wasn't but intentional at all, but you can see unexposed, most of the probability density is pushed up against 0. But for the exposed group, there's actually pretty good support, pretty good coverage. And then once you match, you can see the probability, propensity distributions, I should say, overlap almost completely. It's an interesting little kink there right around 0.5, which probably has to do with the matching algorithm. But more importantly, so generally looking at covariates, you want to then go and check that you've achieved your goal of getting balance. So in the blue, you have the unmatched differences across these different demographic characteristics, so percentage of male, different age categories, race, ethnicity, education, and so forth. And then in the orange, you see after matching the size of those differences. And so the dotted line here is, that's a standardized difference of 0.1. So generally, does a pretty good job, brings most of the differences down to at least 0.1 or less. Okay, estimating the treatment effect. So a lot of research on this topic, a lot of different approaches you could take here. So the general recommendation is that once you come up with your matched set, you have your exposed, unexposed, you want to incorporate the propensity score into the analysis somehow. And the basic idea here is that the propensity score and the matching isn't going to be perfect. There might be some residual confounding. You can add that score into the model. It's sort of a proxy for all these variables you're trying to control for. It might give you a little bit of extra bias reduction. There's three general ways that you can accomplish this. So the standard way would be a regression adjustment, right? You have a model where you regress your outcome variable. Let's say we're talking about conversions here, onto some indicator of exposure or not. And then you include either a stratified version of your propensity score, usually quintiles, or you can include the raw version. There's also some recommendation, came from Rubin, that if you run your diagnostic tests and there's still some imbalance or lack of balance on particular covariates, you could also throw those into the model too, just to be safe. The last two approaches, so I'm going to highlight these. They're slightly different than what I just described. So stratified analysis is a classic epidemiological method for controlling for confounding, right? You take some confounder, you stratify it again. I think it was Cochrane that suggested quintiles. And then you estimate the treatment effect, right? Comparing exposed and unexposed within each of those strata, weight and pool the results. Now, you could do this after matching, but generally it's recommended, or this type of analysis came out of the idea that you wouldn't actually do any matching. You would just do more of a classic epidemiologic style analysis where you would do the stratification. I haven't really seen that used either way much in this literature, but that was something that was talked about early in the development back in the 80s and 90s. So inverse probability of treatment weighting, this is a method also that has become, I see this actually pop up in marketing now more and more. It's often referred to as the synthetic control method. And essentially what you do is you fit a regression model and you weight it by the inverse probability of the propensity. And again, typically this is done without matching. So that would allow you potentially to get sort of inference over the entire range of exposed and unexposed. You could also do this on a match sample. My general preference, if it's possible, is to find a good match and basically create sort of, again, like a true quasi-experiment where you have a treated group, exposed group, and then you estimate average treatment effect in the standard way. Okay, limitations and cautions. So, as I've said multiple times, this is obviously a quasi-experimental method, not an experimental method. And the ability to produce valid inferences here depends on how well you can account for key confounding variables. Again, I think theory is really important here. But it ultimately comes down to, I would argue, can you rule out all plausible alternative explanations for your findings, okay? And I want to emphasize this because I feel like in the statistical literature on causal inference, that point gets lost a lot. And it's actually really what causal inference is all about. And again, I think having some theory is very helpful to really think about what are the potential confounds here, what are the potential threats to validity. Your inferences are potentially based on a subsample, right, of common support, so this area where the propensities overlap. If you think about, you go back to the sort of machine learning ideal where you have a very small area of overlap. Imagine trying to do propensity score analysis in that region. Maybe if you have big enough data, you could, but in a sense, your inference would be on a subpopulation that's right around 50-50. And so it's a little bit of a contrived situation in that way, and it's going to, it's always sort of seemed a little odd to me. So that's why you really want to make sure you have good coverage. General literature research, simulation research suggests propensity score matching is probably pretty consistent, pretty good for directional inference. So is there an effect? Is it positive or negative? There's a lot of mixed evidence about how easy it is to recover the size of the treatment effect that you're looking for. So it's, unfortunately, there's no, again, silver magic bullet, pick your preferred metaphor for this particular problem. And definitely your results are gonna vary. And so probably the best thing you can do if you wanna implement this, given the use cases that you're dealing with, is create some synthetic data that are similar to the data you're working with, relevant to your use case, and really just test different approaches and do sensitivity analysis. See what happens by changing your matching algorithm. See what happens by changing model specifications, different interactions and things like that. I wish there was a simple and easy cookbook for this approach, but it's generally, it's gonna take a little bit of work up front to get it to a place where it's probably gonna be useful in your particular use case. Just some resources. So perhaps not surprisingly, there's not a ton of packages in Python. This is a method that comes out of statistics, so that's where most of the packages have been developed. But there's two packages I found. There's Causal Inference, which looks like it was built about 3 years ago. I don't think there's been a pull request in about 2 years, so maybe you want to make a pull request. I don't know. PyMatch is kind of in the same situation. It looks like it was built out for a particular project. It was developed about 2 years ago, and I'm not sure if it's even being maintained. If you want to just dive in, you're not hung up on using Python, you can check out Matchit, which is an R package that does a lot of this stuff. Theory and practice, the original article by Rosenbaum and Rubin, it's probably worth checking out. And then more sort of applied articles. This article in particular, Peter Austin at University of Toronto has done a ton of research on propensity score matching, both different matching algorithms, different modeling approaches, and so forth. And then this last article is a really nice overview of really the issues you need to think about at each step in this process of trying to do a propensity score match. Okay, I think that's all I have. Happy to take questions. Yes?
So like when you build the propensity score, is it like you care more about minimizing the error in the training data set instead of the testing data set? Is that true?
That's a good question. You're really concerned with including and capturing all of the potential factors that could confound. So it's a more traditional statistical model where I'm just trying to build the model that I think best represents how some independent variables or some predictors relate to some outcomes. So when I've used this, I do a very, I often use a light amount of regularization. I do a test train, but I'm not really trying to optimize anything, to be honest. I'm really just trying to, I'm focused more on what variables are in the model and whether or not those are the right variables to potentially eliminate any confounds or selection biases. So you could use, scikit-learn. It's not going to, be a detriment in any way, but it's not necessary either. You could use stats models, just build a simple regression model. Yeah. Yeah.
I noticed that you're using the propensity score to match the covariates, even though that's not like explicitly in the cost function of the whatever propensity score model. So can you talk about why it's used as opposed to a model where like covariate matching is specifically in the cost function?
Yes. So, let me repeat your question back to you, because I think what I hear you asking is, right, what is the advantage of a propensity score versus just matching on covariates like in their original form? Yeah, that's a great question. So, yeah, and originally it's kind of the traditional approach is like you have, 5 background factors, and you just try to match almost exactly or even in straight across those. But quickly you run into limitations on practically how many covariates you can match on. And one of the real advantages of this approach is that you could have, 10, 20, 30, 40 covariates that you could theoretically be matching on simultaneously. So in a way, it's more efficient. It gives you more bang for your buck. And in some of the projects I've done where we have a lot of potential background information, there's just no way you could do like a straight one-to-one or even like a sort of, I guess you could call hyper-stratified match. Does that kind of answer your question? Yeah. And like I said, the way I've always thought about this is really nice is you're using this model to take all this information and just get it down to one number. And then once you've got that one number, the matching is a lot easier. Oh, sorry, that's not a question. That's 5 minutes left. Okay.
Yeah. So does this generalize at all to non-binary outcome variables? Or does it easily?
In terms of, so the propensity model, let's say you had a control condition and 3 treatment conditions, or you're talking, or like a condition, yeah.
You can imagine
Yeah.
died or recovered somewhat, or,
Yeah. Yes, you could adapt it to that situation. You would basically, I actually haven't seen a lot of work on this. I think right now the general approach would be you would, let's say you had 3 treatment conditions. So you would build, 3 minus 1 propensity models, sort of, right, one against each. Or I guess you build 3, one treatment against control. I've not seen it done where the outcome is some continuous variable that represents maybe exposure in some way. Is that what you're getting at?
Your case, right? That someone became a marginal customer, a great customer.
Yeah. I think you'd still need to like categorize them in some way to create sort of those buckets, those levels. But you could do it theoretically, yeah.
So you have talked about coverage of propensity score a couple of times. So my question is, if there's not enough coverage, is it possible to, do something to increase it, or that's not even option?
Yeah, that's a good question. So you could try different model specifications, frankly, to see if you could increase that coverage. Probably in a situation like that, your best option is something like inverse probability of treatment weighting, so that you could use the entire sample. And I think that's why that method has become so popular, because it doesn't need that overlap. But yeah, to some degree, you're kind of stuck. I mean, in an interesting way, it's that model's telling you that these are just 2 very different groups that maybe aren't comparable.
There's another package in R called Twang that uses boosting
Ah,
to.
okay.
So I just wanted to mention that.
Okay.
I know you said they're usually be different.
Yeah. What is it called again?
Called Twang.
Twang. Okay. Yeah. And I should say I've found 1 or 2 papers that you try to use boosting to build a propensity model. Not a lot out there, but yeah, that's good to know.
Gotcha.
Other questions?